All right, we're going to work our way through a couple interest problems, and we're going to start pretty basic here. Some of the variables that we're going to set up, P is going to be our starting amount, which is principal. And again, interest, we're just going to take that principal times the rate times the time, and we're going to assume that this is just 1 year. So when we set this one up and we go through, we're going to do a little proof to solve this. So if P is what I start the year with, I want to find how much money I'm going to have at the end of 1 year. So to do that, I would have to take my starting amount, and then I would have to add my interest. And again, my interest was P times R. Well, a simple factoring of this, I can pull a common term out, P in each of these two terms. So I'm going to end up with P and 1 times R, or 1 plus R. So this would be a quick formula that I could use to find how much money I have after 1 year. Well, of course, I want to figure out what happens after that. So we'll go to 2 years. 2 years says we would take our starting amount at the start of the year, which is what we ended year 1 with, and we would have to also do interest, which would be that amount times R. Well, if we factor this again, this time we can pull a P1 out, and we'd be left with 1 plus R. Looks fairly similar, but we also found what P1 was, and that was this part right here. So P1 can also be rewritten as P times 1 plus R times this value, 1 plus R. And since these are the same term or the same factor, we can just square that. So let's do one more. We want to find out what we have after 3 years. So we would have to take what we had after 2 years, and then also take that amount of interest. So, like we did before, we can factor out a P sub 2. We're left with 1 plus R. And again, P sub 2, our previous line, simplified down to this form. So I could have P 1 plus R all squared times 1 plus R. And obviously, again, same factor, second power, first power, third power. And this can go on and on and on as far as we need to take this. So there's a little bit of a shortcut here that we can simplify in terms of T for years. Here we had first power, or first year, first power. Second year, second power. Third year, third power. So we can just follow our pattern, and we can take our principal and then do 1 plus our rate and raise that to time. So this would be our formula if we wanted to find our compound interest, if we compounded it 1 time per year. So that's where we'll start with this one. And then we can actually take this up another level, because obviously some options are going to start occurring where it's going to happen more than once. So we could compound quarterly, we could compound monthly, we could compound daily, and so it's actually going to build off of this equation. So let's set that one up. Alright, so if we started with this general equation, or I should say we just finished with this, one adjustment we can make to take care of compounding more than 1 time a year is split this up into parts. So one thing I could do is do this. We could say our ending amount is going to equal our principal, and then 1 plus, now since the annual interest rate is what's usually given, we're going to split that up n times. So however many times a year they compound the interest. And then we add the n up here. So now this would be the format for compounding. So this would be the formula we would use if it's 1 time a year, this would be the amount or the formula that we could use if we compound it more than once a year. Now, let's take that to the extreme. Well, actually, we should look at one other thing first. The n value here is the number of times that the compounding happens. So it's quarterly, n would be 4. If it's monthly, n would be 12, and so on. All right, like I said, let's take this one step further. And we're going to do a substitution here to add to our proof. And here's what the substitution is going to be. We're going to rename n and r. We're going to do n over r equals m. And then I'm going to do a cross multiplication here, which is going to lead me to say that n equals r times m. So I'm going to take r times m and substitute that in on the denominator here and the exponent here where you see n. So that's going to give us this. P 1 plus r over, and here's our substitution, r times m. And then up here, the n becomes again r times m. Now there's a little simplification that takes place here. R cancels here and here, so we get a 1 on top. And that's going to simplify a little bit further into the 1 over m. Now, if I want to get all of my m's kind of grouped here, we're going to use one of our steps that we use when we're doing some factoring with exponents. And here's what I'm going to do. We're still got p times this, and this whole factor is raised to this power. Well, I can split this exponent and make it look like this. And I'm going to raise this to the m, and then raise this entire thing to the tr. Again, because an exponent raised to an exponent is just multiplied. So that's where we simplified this. All right, now we're going to take a look at some of the effects that happen when this m starts growing a little bit. So if we start plugging some values in for m, we're going to look at what's inside the brackets here and what happens to that value. So 1 plus the reciprocal of m, or 1 over m, raised to the m power. Now, I've done these out ahead of time just to save some time, but just to walk you through what we're looking at here again, if m is 1, I would put 1 here, 1 here. Well, 1 over 1 is 1, added to 1 is 2, 2 raised to the first is 2. Pretty basic. Let's raise it a power of 10. So now I've got 1 over 10 here and a 10th power. This one plays out to be approximately 2.59374,246. Alright, again, a little overkill on this, but it's going to prove a point. Let's raise it another power of 10. This time when we place 100 in for both of these m values and simplify this, it's going to turn out to be approximately 2.704813829. Sorry, that got a little sloppy. And I'm going to continue the table. And we'll go down a little further here. And we'll raise it one more time to 10,000 for the value of m. And you should see a pattern starting to emerge over on the right side of the table. And let's go one more here. So we'll let m be 100,000. This one takes us out to this. And we could keep going on and let this approach infinity. And as that happens, you start recognizing a little pattern happening here. Value actually starts approaching the magic value that we talked about in one of the earlier videos of e. So, our natural exponential function, which leads us to a simplification of this into being A equals P E raised to the RT. And if you've had me in class, you know, we just refer to it as PERT, as a little mnemonic to help you remember that. R is your rate, T is your time, P is your principal. This will be the formula we'll use when we're compounding continuously. So we've got 3 here. One when it happens 1 time a year for a compounding, once if it compounds more than 1 time a year, and another formula for when it compounds continuously.